Have you ever stopped to think about how the universe builds stuff? You know, everything from the water you drink to the air you breathe? Well, it all boils down to a fundamental set of rules that tell atoms how to connect. And today, we're going to decode one of the most important rules of them all. It really all kicks off with this one simple question. Why do atoms even stick together? What is the force that pulls them into these partnerships that make up, well, everything? The answer, believe it or not, is actually pretty human. It's all about finding stability. See, in the atomic world, you've got the cool kids, the noble gases like argon or neon. They are super stable, totally unreactive, because their outermost shell of electrons is completely full. And it turns out, pretty much every other atom out there just wants to be like them. And this drive to get a full outer shell has a name. Chemists call it the octet rule. Now, octet just means a group of 8. The rule basically says that atoms will do what they have to do, gain, lose, or, and this is the important one for us, share electrons to get a full set of 8 electrons in that outermost shell, which we call the valence shell. Okay, let's actually see what this looks like. On the left, here's a chlorine atom. If you count those little dots, its valence electrons, you'll see it has 7. Oh, so close to 8. On the right, that's its goal, to have a stable outer shell with 8 electrons, just like the noble gas argon. So the big question is, how does it get that one extra electron? Well, it doesn't have to go out and steal one. Instead, it can find another atom in the same boat, and they can decide to share. And this idea, this sharing, is the foundation for almost every molecule you can think of. It's called a covalent bond. So a covalent bond is really just an atomic partnership. 2 atoms each put an electron into the middle to form a shared pair. This pair then belongs to both of them, and that helps each atom feel like its outer shell is complete. It's a total win-win at the molecular level. And here it is in action. You've got 2 chlorine atoms, right? Each one has 7 valence electrons. So watch this. They each share 1 electron in the space between them. Now for the magic part. Let's count for the atom on the left. It has its 6 original electrons plus the 2 in the shared bond. That's 8. And the atom on the right gets to count those 2 shared electrons as well. Bam! They both have a stable octet. By the way, these little diagrams we've been drawing with the letters and the dots, they have an official name, Lewis dot structures. You can think of them as the architectural blueprints for molecules. They're a super simple but really powerful way to see how everything's connected. Now, sharing just 1 pair of electrons makes what we call a single bond. But sometimes 1 pair just isn't enough to make everyone happy and stable. So, to satisfy that octet rule, atoms sometimes have to form even stronger connections by sharing more than 1 pair. Here's a textbook example of single bonds. In carbon tetrachloride, you have carbon in the middle, which needs 4 more electrons, and you have 4 chlorine atoms, which each need 1. So what's the perfect solution? Carbon forms 4 separate single bonds, 1 with each chlorine. It's beautiful. Everybody gets their stable octet. But what about something like carbon dioxide, CO2? If you tried using only single bonds here, it just wouldn't work. The numbers wouldn't add up to give everyone an octet. The solution is for the carbon atom to share 2 pairs of electrons with each oxygen. We call this a double bond, and you'll often see it drawn as 2 lines. And believe it or not, we can take it even 1 step further. The nitrogen molecule, which makes up most of the air we're breathing right now, is made of 2 nitrogen atoms sharing a whopping 3 pairs of electrons. This is a triple bond, and it is one of the strongest covalent bonds out there, which is why nitrogen gas is so stable. Okay, so we've got single, double, and triple bonds in our arsenal. But when you're looking at a brand new molecule, how in the world do you know which bonds to use where? Well, thankfully, you don't have to guess. There's a reliable, step-by-step method for this. Here's our 4-step game plan. First, you just add up the total number of valence electrons from every atom involved. Easy enough. Second, you draw the basic skeleton, just connecting everything with single bonds to start. Third, you take all the leftover electrons and start placing them around the atoms as lone pairs. And finally, if you get to the end and the central atom still doesn't have 8 electrons, you start making double or triple bonds until it does. All right, talk is cheap. Let's actually put this blueprint to the test. Our first case study is going to be carbon monoxide, or CO. Okay, let's follow the steps. Step 1, total valence electrons. Carbon has 4, oxygen has 6, so that gives us 10 electrons total to play with. Step 2, connect C and O with a single bond. That uses 2. Step 3, distribute the other 8. If we give 6 to oxygen and 2 to carbon, oxygen has its octet, but carbon's only got 4 electrons. That's not going to work. So on to step 4. We have to make multiple bonds. And it turns out the only way for both atoms to get a full octet with just 10 electrons is to share 6 of them in a triple bond. Now everybody's stable. So that system works great for neutral molecules. But what happens when the whole thing has an electrical charge? You know, when it's an ion? Let's try to draw the blueprint for the nitrite ion, which is NO2 with a -1 charge. Let's run the playbook again, but with a little twist. Step 1, count the electrons. We've got 5 from nitrogen plus 6 from each of the 2 oxygens, so that's 17. But, and this is the key part for ions, that negative charge means we have 1 extra electron, so our grand total is actually 18. Now, after we connect everything with single bonds and place the lone pairs, we find that the nitrogen in the middle is still short. So for step 4, we grab a lone pair from one of the oxygens and turn it into a shared pair. That creates a double bond, and now every single atom has a stable octet. And what's so cool is how versatile this blueprint approach is. I mean, look at this table. It works for super simple stuff like a hydrogen molecule, for double bonded oxygen, for more complicated things like Na3, and even for ions with a 2- charge, like carbonate. The same rules get you to the right answer almost every time. All right, we have covered a ton of ground. So let's slow down for a second and summarize the absolute key ideas that you can add to your own chemistry toolkit. So what are the big takeaways? First, remember the driving force. Almost all atoms are trying to get that stable octet of 8 valence electrons. They usually do this by sharing electrons in covalent bonds. We draw these molecules using Lewis structures, which are like our blueprints. And to draw them, you always start by counting the total valence electrons. Don't forget to adjust for ions. And then you use single, double, or triple bonds to make sure every atom wins. So we spent all this time talking about how atoms follow the octet rule. But, in science, rules are practically begging to be broken, which leaves us with a really fascinating final question. If 8 is the magic number, what happens when atoms decide to break the rule? Well, that is a story for another time.